What's significant about today? It's our last lecture of the semester. Well, it's been a lot of fun. I actually really have enjoyed it. I hope you guys had a good time. I feel like I was talking to actually one of your colleagues in office hours like earlier this week, and yeah, I think life is kind of too short not to do what you like. So some of you are like, well, I kind of like school, but most of you are here because you have like a plan, right? And this is the means to an end. And so you're figuring it out, and hopefully there's moments that you enjoy, but you get down into life a little ways and you stop enjoying what you're doing. It's time to make adjustments. It's just like pivot and do something different. So I started teaching here in 2007, 2008, and then I kind of came on full time like in 09, 10, probably 2010 full time. So I've been doing it about 14. I think I'm in my 15th year. And I thought, well, I'll just do this for a few years and I'll probably stop liking it and then I'll go find something else to do. But you guys make it so much fun. So 15 years later, I'm still doing it. I'll probably still do it for a while until it's not fun anymore. So thank you to all of you for making it enjoyable. Okay, not everything's enjoyable, but for the most part, it's been a great experience, right? You have a bad exam, I get it. It's not enjoyable, right? But and I get emails from you guys saying that you're not happy about things. It's not enjoyable, but overall, I think it was a really fun semester. So I appreciate that. Thanks for coming. It's not nearly as fun if there's nobody here. So thanks for being present. But yeah, this is our last time together. So last time of lecture. We have an exam, but not all of you will be here on Monday. I understand that. We've had some time to kind of navigate those special situations based upon your calculations. Okay, what does one house say to the other? How's it going? What happens when you eat yeast and shoe polish? Yeast and shoe polish. What's that? A loafer? I like that. Well, yeast and shoe polish also could lead to rising and shining. Rise and shine. What kind of dog do you find in a bakery? A purebred. A purebred. All right. I'll do a couple more on Monday, and then that'll be it. A couple of announcements. So we've got a quiz the last quiz that's due is this week, right? Some of you have already taken it. Canvas is up to date. Canvas grades are up to date. I've spoken with many of you over the last few days. So I think a lot of you have like a really decent picture of where you are, especially if you're kind of borderline or you're trying to decide, am I dropping the final and not showing up or not taking it or going to take it just for fun? I know that sounds weird, but like I've got an OChem exam that I really need to focus on. That's a lot of you. So I would really like not to have to focus on your exam. So, that might be the situation. That's not all of you. Some of you, maybe, hey, I'm just really trying to pass this class. And so I kind of want to know what I need to do to pass. So Canvas is up to date. What's potentially missing out of Canvas is the following. Obviously the final, which is on Monday. But the Chapter 10 quiz may not be incorporated. Your participation points from Monday, your participation points from a review session. If you're not taking the final, those still will count for or against you. So you don't want to miss those. Or you want to make sure you have enough buffer if you miss them that it's not a big deal. Okay? The bonus opportunity that I'm going to hand out at the end of today only is for those that are taking the final. So, okay, if you drop it, you drop everything. You don't like kind of get your cake and eat it too, right? So the bonus opportunity will only count if you're taking bonus opportunity 5 will only count for those that are taking exam 5 or the final. Is that all clear? I'm going to hand out the bonus opportunity today. It's not going to open until Friday morning at 12 a.m. The reason is I want another day for those of you that are trying to figure out your grades to be able to calculate them based upon Canvas. Once you wake up on Friday morning, the moment you take the bonus opportunity, Canvas will be off. Does that make sense? So today, tomorrow, even Friday, and the bonus opportunity won't be due until Monday at midnight. So you could take it after the final. If you want to keep your Canvas preserved so you can see your grade, right? Does that make sense why I'm doing that? So it'll be open until Monday evening, the bonus opportunity. So if you're trying to calculate your grade, Canvas will be accurate until the moment you take the bonus, Canvas will be inaccurate because it's going to be counting points that shouldn't be counting. Okay? That's the easiest way to explain it. If you have a question, just email me. Okay? I have this like really complicated Excel sheet that some of you saw this afternoon with formulas and everything. So I have it, I think, pretty dialed in with respect to making sure things are accurate. And then the last one, I'll say it again, 89.5 and up is what? An A. And an 89.49 is what? It's a B. It was day one. It'll be that when I finalize the grades. We've kind of said the reason and the rationale behind it. I just want to make sure that everybody understands the why. Okay. So this is where we left off. We left off on hearing. Then we need to cover equilibrium, and then we'll get into balance. So to finish out hearing, the how we hear, someone explain to us, how is it that we hear? What are we actually interpreting? Sound waves, vibrating air molecules, ultimately vibrate a membrane that vibrates 3 bones attached to another membrane that sends ripples in a fluid that pushes on hair cells that actually are connected to a neuron. And when the hair cell moves, there's a mechanical gate that opens and an ion moves in and you cause an action potential. It's that simple. We'll go through it again, but hopefully you kind of followed that, right? If I explained that to you day one, most of you would have been lost. But if you can just at least understand what we just said, we take sound waves, air molecules moving, move a membrane, a mechanical vibration, it moves 3 bones, pushes on another membrane, sends ripples in a fluid that impact hair cells mechanically that move, opens a gate, a mechanical gate, and an ion comes in. That ion disrupts the electrical potential, sending an action potential down the nerve that goes to the brain. How many of you actually followed what I just said? Okay. Day one, you probably would have been like, what the heck is he saying? So it's like, at the end of the semester, we kind of synthesize all this information. It's kind of cool. And I think that's one of the reasons that this section is actually very straightforward, is you have a tremendous amount of background. And I'd like to believe that's what's going to happen in 202. You have a tremendous background in 202, the second semester of this class. And you'll be in other systems. Of course, you're going to be in other systems. But the first thing that we do in 202 is we talk about tissues again. Tissue organization. Simple squamous, cuboidal, columnar. We talk about that again because we need to use some of those in different systems that we're studying in 202 that we didn't study in 201. So we laid a lot of foundations in 201. You're going to leverage a lot of that foundational information in 202. The time of like the 181, 182 and general chemistry is fading. There'll be elements of that coming back in 202, like when we talk about the nephron or kidneys and how they work. You kind of need to understand some chemistry. But the examples are really straightforward, right? Cardiac action potentials, the way cardiac muscle works, right? You already know about cardiac muscle. So I think 202 tends to be a little bit smoother for students because you're building on the foundation, just like this unit is a little smoother than Unit 1 or Unit 2 or even Unit 3 or 4. All right, so we talked about how this works. We've got this diagram that we walked through. This diagram shows the eardrum, or the tympanic membrane, vibrating these three bones. Here's our oval window that's connected to this fluid on the other side where we get those ripples. Those ripples will push down through these channels, ultimately vibrating what we refer to as the basilar membrane. The basilar membrane is this membrane, base membrane or basal membrane. On the basal membrane is housing this hearing organ, or what we call the organ of Corti. That organ of Corti has a tectoral membrane on top. We talked about this on Monday. It has, coming up from the basal membrane, it has hair cells that actually have neurons attached to them. They're embedded in the tectoral membrane, and when the tectoral membrane moves, these hair cells actually move. So mechanistically, if we zoom in, these are the stereocilia, or the hair cells, that are found within the hearing organ. So at the bottom, this is the surface of the hair cell. They have these protrusions. At the top of the protrusion, if you zoom in on this little box diagram that's here, there is a channel embedded in this membrane. This is a mechanical gated channel. It actually has attached to it this filament. This filament is known as the tip link. It's a fine, stretchy protein. It has elastomeric properties to it. And when the hair cells are deflected, like you see on the right image, the hair shifts, the tip link pulls open the gate, and because this is in this space of the cochlear duct with endolymph that's high in potassium, that potassium ion is outside of the cell in high concentrations. This is the complete opposite of what we learned about in the regular nerves. And potassium rushes into the inside of the cell, causing the depolarization event, which is kind of cool. And instead of sodium here, we switch out, and potassium has an opportunity to cause the action potential. That signal of ion change, you know the rest of the story. Inside of this hair cell that's connected to the back of a neuron, you get propagation of the depolarization event. So if you have any trauma to the tip link, you have any trauma to the hair cell, you have any trauma to the organ of Corti or this tectoral membrane, there are no basal cells that regenerate any of this tissue, and hearing loss takes place. So in this image, what we're trying to portray is this cochlea unwound. So imagine the cochlea kind of unwound. You can see the scala vestibuli on top. You can see the scala tympani on the bottom. And then you can see the cochlear duct right in the middle. And the scala vestibuli and the scala tympani actually connect at this section known as the helicotrema. And the helicotrema is on the distalmost end of the cochlea. So these sound waves that come from the vibrating stapes from the oval window, the sound waves move in this direction. They eventually come back this way, and then there's a second membrane, second tympanic membrane, that absorbs the sound wave or the ripple so that it doesn't bounce the other direction, and you don't have this echoing effect. And as it moves from proximal to distal, and you have these ripples, you vibrate the cochlear duct beneath the scala vestibuli, and in effect, you vibrate the basilar membrane, which is the bottom part of the cochlear duct. And when you do that, that's what actually moves the hair cells within the tympanic membrane. So this helicotrema is important. Our secondary tympanic membrane is important because it absorbs the waves so you don't ricochet back and start hearing this echoing effect. And the reason that we stretch this out and roll it out is so that you can kind of appreciate where the zones are where you hear certain pitches. So these pitches or frequencies that we talked about on Monday, if you imagine this coordinates with the diagram above, are low frequency sounds, 20 to 800 hertz, that's bass, that's low bass. These are found here on the distal end. And you can see these waves here on the distal end. The medium frequency, 1500 to 4000 hertz, is right in the middle. And then on the proximal end are the high frequency sounds, 7000 to 20,000 hertz. So if you have patients that have high frequency, high pitch hearing loss, that's at the very beginning of the cochlear duct. If you have patients that lose a lot of bass sounds or low frequency, that's at the very distal end or the very end of the cochlear duct. So 2 different types of deafness. So if you're going to be taking the final, this might be something to pay attention to, this image. We've got 2 different zones. We can either have conduction deafness or we can have sensorineuronal deafness. So conduction deafness is really referring to anything of the outer as well as the middle ear. Everything that's in green. Conductive loss. Anything here. So on the other side of the eardrum or the tympanic membrane, including the ear ossicles or even the stapes and the round window, wax blockage, right? Remember, we had ceruminous glands that we talked about in the integument system. We talked about modified sweat glands. And we had 2 different types of modified sweat glands. One was what? What's that? Not sebaceous. Modified sweat gland. Mammary and ceruminous. Mammary glands make milk in females, right, from blood filter. And instead of making sweat, you actually make a milk. And the second gland that's a modified sweat gland is a ceruminous gland that's found in the ear canal that makes wax. And so the wax is pulled from a lot of the lipid debris from cell that are being recycled, creating a waxy layer inside of your ear canal to keep a lot of debris out and away from the tympanic membrane. All right? So wax blockage, conductive deafness, a ruptured eardrum, or otitis media. So that's media that's found within these middle ear ossicles. And you get a media that forms there and kind of prevents them from moving. Or you have a sclerosis, like an inflammatory, almost arthritic type of condition of those bones. All of these conditions would be a conduction deafness. Sensorineuronal is anything on the inner ear. So anything with the tectoral membrane, anything with the nerve, anything with the hair cell, anything with the tectoral membrane. These would all be considered sensorineuronal. Now, ultimately, where does this go? Well, it projects from, like we talked about, the cochlea and the vestibular apparatus. You have the vestibular nerve and the cochlear nerve, and they merge and innervate into the brainstem. As they merge, they form cranial nerve 8, right? Vestibular cochlear nerve. And then look at all of these areas that you receive follow-up innervation, right? So remember, do you remember the inferior colliculus? The inferior and superior colliculus, when we talked about the central nervous system? This is what helps with hearing. The superior was vision. The inferior is the hearing, where you can kind of determine if a sound is coming closer or if a sound is moving further away. Remember the example I used was like an ambulance. Even like kids can tell when an ambulance is coming closer to the house versus further away from the house. And that's a function of information going to the inferior colliculus. And then up to the thalamus, and then up to eventually the primary auditory cortex, where you're going to start interpreting that sensory information to say, oh no, that's not an ambulance, that's actually a police car, right? Because they have different sounds. All right, let me just show this real quick, kind of cute video, just to sort of summarize everything. Oh, sorry.
Hearing is one of your five senses. It's called the auditory system, and it does more than just take in sound. So listen up.
Would you like a drink of water? What? Would you like a drink of water? What? You can't hear me if your music's too loud. And besides, that's bad for your hearing. Why? Because loud sounds can damage your ears. How? How does your hearing work?
Hearing begins with sound. When you make a sound, you create energy in the form of sound waves. A loud sound has taller waves than a soft one. Those sound waves eventually enter your ears. Sound travels down the ear canal. The ear canal is about 1 inch long, and at its end is a thin piece of skin called the eardrum. The eardrum is stretched tight, just like the top of a drum. When sound waves hit the eardrum, it begins to vibrate. That vibration makes 3 tiny bones in your middle ear begin to move. These 3 tiny bones are known as the hammer, anvil, and stirrup. And that's kind of a bootleg. These 3 bones transmit or move the sound along to the inner ear. They also increase the force of the sound waves. Sound waves then move into a snail-shaped structure in the inner ear called the cochlea. The cochlea is filled with fluid and made with 17,000 tiny hair-like tissues called hair cells. Sound waves move through the fluid and the hair cells bend. The movement of those hair cells stimulates the 30,000 nerve fibers leading to the hearing nerve. That nerve carries the signal to the brain, and the brain figures out what the sound is. It's important to protect your hearing from loud sounds. Muscles in the middle ear protect the ear by stiffening the eardrum and the movement of the hammer, anvil, and stirrup bones. But sudden loud sounds can break and damage the hair cells in the cochlea, and even break the eardrum. And continued loud sounds can also damage those tiny hair cells. So be sure to wear hearing protection like earmuffs or earplugs if you're going to be around loud sounds, and turn down the volume on your headphones. Because if your hearing is damaged, it can't be made all better. About 200,000 Americans are deaf.
Okay. So obviously it's a pretty elementary video, but I think I like to show these videos so you can at least kind of see in motion what it is that we're talking about on still pictures and with the words, right? And I think that last little piece of, protecting your ears, now you probably can appreciate, well, unlike the sensory cells in gustation and olfaction, hearing sensory cells don't have a regenerative cell type. And so once it's damaged, you can't regenerate it. So you cannot repair that hearing loss. And that's why we spend so much attention. I don't know if you noticed, but that was like taken from some like Idaho public broadcasting information, public health type of information. And especially today with, the amount of audio equipment that everyone has that they're carrying around with, earbuds and different types of headphones and noise canceling where, we get great sound, but I think we might be seeing a lot of hearing loss in the future. Okay, well, the story doesn't end with the ears on hearing. The last little piece before we move to vision today is equilibrium. So this is a familiar picture. We looked at the outer ear, the middle ear, and the inner ear. When I introduced today's lecture, it was the schematic diagram. This schematic diagram is a little bit more true to life and kind of matches that video that we just looked at. And instead of focusing on the cochlea, we're going to look here at the vestibular apparatus, which is up here, which includes these semicircular ducts or semicircular canals. So this structure is for maintaining balance. We've got the vestibular apparatus that's made up of these semicircular ducts or these semicircular canals. And if you notice in this picture, they're oriented in an X, Y, and Z plane. And the fluid moves in these canals either in a Y direction, in an X direction, or in a Z direction. And as that fluid moves, it's also going to push on hair cells, but those hair cells are actually found encased in a structure. So it kind of pushes on a structure. It looks like a gelatinous structure, and the hair cells are found within there. But the idea is you can determine different things based upon different structures. So if we look at our vestibular apparatus and our semicircular ducts, we're going to talk about things like angular acceleration. So angular acceleration detects the rotation that's taking place, or the rate of rotation, like when your car is turning a corner. Okay? And you can tell. Like if you close your eyes and you're driving in a car, you notice when you make a turn, right? You can determine if you're turning left or if you're turning right. Right? It's very convenient if you're being kidnapped, right? And you're blindfolded. Like you can tell where you're going. You can count the turns. Well, you also can determine whether you're stopping or starting or accelerating. And that's the saccule and utricle that help information about static equilibrium and linear acceleration. So like you close your eyes, you come to a stoplight, right? Someone else is driving, of course. You're in the passenger seat. You're closing your eyes. You come to a stoplight. You know that you're slowing down. That's the saccule and the utricle that are giving that information. Okay, very helpful information for our daily lives. Helps balance and equilibrium, keeps us on our feet, prevents us from falling down. Even if we're not getting visual cues, you actually have the ability to understand in three-dimensional space where you are. Pretty important, okay? All right, so let's look at this. You can see the macula utriculi here and the macula sacculi here. So this one is a little bit more close to the cochlea. This one's a little bit more close to the semicircular duct. So the utricle is closer to the ducts. The saccule is closer to the cochlea. So if we specifically look at the saccule and the utricle first, you can kind of see this diagram that kind of explains that, you know, the saccule, the macula sacculi is for the vertical, and the macula utricle is for the horizontal. And so we have our stereocilia. They're sort of embedded, encased in this otolithic membrane, which is like a gelatinous membrane full of calcium crystals. This membrane, which kind of, you know, has a substance to it that coats and covers the hair cells. You also see supporting cells there. But again, what's missing? What cells are missing? Basal cells are missing here as well. So trauma and damage to these cells, non-regenerative. As patients age, some of them do wrestle with equilibrium and balance issues. And there can be trauma that takes place either on the hair cell, on the otolithic membrane. The otoliths, like anybody, this is kind of apropos for like Thanksgiving time. Anybody have a grandma that makes like Jell-O with fruit inside of it? No? Somebody? One person? Okay, all right, at least one person. Midwest, or where are they from? Alabama. Okay, perfect. All right, so Alabama Jell-O, right? So you have the Jell-O, you've got the, you know, the fruit that's suspended in the Jell-O. That's how I imagine this looks. But instead of the fruit suspended there, these are crystals of calcium carbonate, and they're otoliths. They give mass or weight to the otolithic membrane. So in the horizontal direction, right, the utricle, that's when you move from the red light to the green light and you know that you're starting to move, or when you're slowing down. And then in the vertical direction, the saccule, same thing. You can see over on the right picture the orientation of the saccule, giving you information about, you know, you can tell when you're kind of inverted, right? If you know, When's the last time you were inverted, right? Like you don't do this every day, but like when you're a kid, right? You would do a handstand, or you're on the jungle gym, you're upside down. You're getting cues and information. Even if you close your eyes, you know where you are in position in space based upon this information, right? Where this becomes a little problematic is how many people like surf or boogie board or in the ocean grew up. Okay, so you get taken out and you're upside down. Sometimes it's kind of hard to figure out which way is up, which way do you swim, right? Because now you're disoriented and you don't have as much of the gravitational force giving you the cues for the otolithic membrane. It doesn't sag as much, so you just kind of don't really know which way is up, okay, in those kinds of situations. Make sense? So, trauma to the otolithic membrane, bless you. Abnormalities or changes in the otoliths themselves, the hair cells, any of these things can impact the way balance and equilibrium can be detected. Yeah. So the question is about vertigo. So this, as well as the semicircular ducts. Okay, so the semicircular ducts are usually more implicated in situations of vertigo. Vertigo is a state where you feel like the room's moving or spinning. You feel dizzy. You feel unbalanced. It's really less about the saccule and the utricle. It's more about these canals that have fluid flowing. And so this is, if you sat here and we did a little experiment and you spun around like 2 or 3 times, I would do this, but I've done this in the past and I had somebody fall. And then the university said, like, that's like a hazard. You shouldn't do this experiment anymore. But you could do this at home, okay? You've done this at home. You spin around in a circle 10 times, you close your eyes, and then you stand there and you still feel like you're spinning because the fluid in that semicircular canal or that semicircular duct is still moving. And if it still moves, you can see these pictures, slightly different orientation, but very similar concept. The jello here is more contained. It's what we call a cupula. So this cupula is this gelatinous material that covers underneath the sensory cells, these hair cells. Collectively, the whole structure is referred to as the crista ampullaris. But as this fluid, this endolymph moves, the cupula will deflect, push on the hair cells, and that fluid in that canal doesn't stop moving the moment you stop spinning, right? It still goes. And so after a little while, that fluid slows down, and then the room comes to rest. So what would cause vertigo if the fluid isn't really technically moving, right? You could have problems associated with these hair cells. You could have issues or abnormalities associated with the entire crista ampullaris where it just sort of is sagging when it shouldn't be sagging. The other thing is, as we age, the endolymph starts developing its own calcium carbonate crystals or debris. And so as the fluid even just moves a little bit and sloshes, right? If there's otoliths that aren't supposed to be there, or calcium carbonate that's not supposed to be there as we get older, it can actually deflect on the cupula when it's not supposed to. You're just kind of getting up from a chair and you go like this, and all of a sudden the fluid is moving and pushing on that, and you're like dizzy all of a sudden. You haven't really even spun. So that's where the vertigo comes from. Really more of the semicircular ducts. Great question. So where do these images, or where do these projections go? These projections actually shouldn't surprise you as we kind of finish out the semester. You can see the vestibular nerve to the vestibular calcular nerve, many different innervation points, right? We've got motor coordination over to the cerebellum. We've got compensatory eye movement. We've got the thalamus, which is the relay center, up to the vestibular cortex, awareness of spatial orientation and movement. Now, these pictures, these two pictures that I showed you today, don't worry about those for the exam. I'm just trying to synthesize older information of where we've been so that you can kind of appreciate why we talked about some of these in the central nervous system and where, like for example, if you remember back to one of the purposes of the cerebellum being motor coordination, why? Well, because it's getting information from the vestibular apparatus. It's not the only thing getting information, right? Look at where all of the signals come in for balance. Balance is really important, really key, right? If you're foraging for food and you're on the ledge of a really high mesa, you need to have good balance. Otherwise, that's your last meal, right? So, I mean, some of these things make sense when you kind of consider what's the purpose of having multiple innervation points on information like balance. It's just something that we take for granted, especially when you're young and you don't have balance issues. But if you ever had a head cold, you ever have vertigo, you can appreciate, many of you work with patients where they have balance issues. So it can be very, very compromising. Questions in the back?
So I don't know 100% all the words, but like the structures that have to deliver, we talking about like spinning and being upside down and stuff. Are those almost like more, not like advanced, but like more developed in people who like dance or do gymnastics or like who play a sport where they're upside down a lot or like spinning or that, or is it kind of
That's a great question. So the question is to repeat for the recording. The structures in the inner ear that are responsible for equilibrium and balance. Like we've got semicircular ducts, we've got the vestibule, the saccule, the utricle. The question is, are they more developed in individuals that do types activities, physical activities that require tremendous amount of equilibrium and balance? And you used examples like gymnastics and ballet. And it's funny because I have 4 kids, and one was a gymnast, one was a ballerina, and 2 were soccer players. I would actually say that, for elite athletes, it's always a question of like that fitness. Is it genetic or is it, training? And the best that we can come up with from the exercise science world is it's probably a little bit of both. And so, there are people that are naturally, better at certain activities, and so they gravitate towards those activities, and they train for those activities, and then they get better. But I would argue that there are probably lots of folks in this room that have tremendous capabilities in balance and equilibrium. And if you think through some of the daily activities that you do that you're familiar with, you've mastered some of those activities because you've practiced them, right? But yeah, naturally, just like any elite athlete, there's going to be some natural predisposition to it, some genetic coding that says, they have a little bit more lean body mass, or their biomechanics on their right arm are a little bit different, and they can throw the ball a little harder, right? So they gravitate towards pitching the ball versus swinging a bat. So it's kind of that nature versus nurture question. It's a good one. Don't have a great answer for you, but in those activities, the training of these structures is paramount, right? So I mean, just for example, like one of my daughters that was did professional ballet. And like 2 years ago, we were in London together because she was competing in a competition there for like 2-3 weeks. It just never, and she wasn't the best one, I'll be honest. Like she was really good, but when you get to that level, it's like, it's unbelievable the talent that you see. And some of the things that you see on the stage, like I almost threw up. I'm like, how are they not like vomiting after like 17,000 spins? And then they stand there and look at you, and you're expecting them to go like, and they're just like, and I'm like, so, there are what my daughter would share with me is there's a lot of training like in ballet where you pick a point out in the audience to look at. So when they do their spin, they come back and look at that point at this, and they're ignoring the other cues and but the fluid is still, my point was to her, was like, the fluid's still moving, babe. Like, I know that you're not seeing this stuff over here, but from the physiology standpoint, the endolymph is still moving. Like, your endolymph, you're not hitting the pause button on your endolymph. I know that. So, but they're training past that, right? You have elite runners. You have elite runners that can run through the pain, right? And you've heard that. You've heard people, you've probably done, there's probably athletes in this room where your coach would help you, I'm going to use that word lightly, help you work through the pain, right? And so it happens, and you train and you get past it. All right. All right, our last little section today is vision. And I wouldn't say that that we've saved the best for last, but I mean, let's be honest. We are visual creatures. There's no question about that. Right? No other creature on the planet has fashion. None of them care, right? They're on social media to decide what they want for Christmas. What slacks are in style, right? Is it a cuff? Is it tapered? Is it high waters, right? We're very visually focused. But if you think about how we interact with our environment, having visual acuity is actually really helpful, right? Makes us the top predator. There's no question about that. We have very acute vision. Now, compared to some other species, our chemosensation is not nearly as good. But when it comes to vision, we have really good vision in the mammalian kingdom. Now, there are other animals that have different adaptive vision, like night vision for nocturnal creatures, which is kind of cool. Okay? But if we're sleeping and that's when a lot of bad stuff happens, and so we stay away from that, we don't need a lot of night vision. If we're hunting and foraging in light hours, we need visual acuity. And the benefit of visual acuity is it comes with color vision. Right? So there's some things that make sense when we look at how we're structured, why we would actually be designed the way we are. All right, so some review from lab, a little bit of review from lab, just kind of getting us warmed up on this last little section of vision. We've got our eyebrows, we've got our eyelids, the palpebra is what that's referred to. You have your lateral and medial commissures. That's actually where the eyelids come together. It's the medial commissure and the lateral commissures. The conjunctiva, that's the covering, the mucosal membrane over the eye, kind of what you stick your contact lens onto. Then we have this lacrimal apparatus. That consists of the lacrimal gland, which are lateral aspect, superior and lateral to the eye. And every time that you blink, a tear is released out of the lacrimal apparatus and crosses over the eye to the medial commissure and drains into the nose every time you blink. And that's just washing it. There's lysosomes in there. There's enzymes. It's keeping that surface clean because it's exposed to the outside environment. So there's a lot of potential for viral, bacterial, fungal contaminants to happen. This is one of the reasons, in flu season, we tell each other, don't rub your eyes. Remember in COVID, they kept telling you, don't touch your face? But the big one is don't rub your eyes with your hands because there's stuff on your hands and it's getting straight into that membrane. Now, this nasolacrimal duct that drains right to the nose, this is the reason that when you cry, you get a runny nose because those tears have to go somewhere, so they drain into the nasal cavity. Okay, so that's what's responsible for a runny nose when you've watched a chick flick. Okay, we watched Sleepless in Seattle last night at my house. That's right. I watched a lot of chick flicks in my day. All right, what makes up the eye? Tunics. Tunics is a word from the Latin that means coat or covering. We have 3 tunics. 3 different coverings that we're going to talk about. The tunics are the tunica fibrosa, the tunica vasculosa, and the tunica interna. We've got an optical apparatus and a neural apparatus. The optical apparatus handles the light that comes in, and the neural apparatus takes that information and creates an electrical signal to the brain for you to interpret what it is that you're actually seeing. These three tunics are showcased here. We've got the sclera and the cornea within the tunica fibrosa. The sclera is the white part of the eye. It's made of dense, collagenous connective tissue. To kind of revert back to Unit 1 when we were talking about different tissue types. And then the cornea. The cornea is the clear covering on the front of the eye where you actually place your contact lens, right on top of the cornea. The cornea is avascular. So if you've ever had allergies or you had a rough weekend, you woke up with bloodshot eyes in the whites of your eyes, you can actually see blood vessels and they're really red. That won't happen in the cornea because the cornea has to stay clear to allow light to pass through it. So the cornea is avascular. It's the only place in the body where there is actually no blood vessels is the cornea. It's one of the reasons one of the most successful tissue transplants in the body from human to human is what? Corneal transplants. Right? No rejection. There's no blood vessels. There's no cells there. It's completely clear. It's just connective tissue. Tunica vasculosa, also known as the uvea. This is made up of the choroid, the ciliary body, right here, and the iris. The iris is the colored part of your eye. And then the tunica interna. The tunica interna is basically the retina, which is the back of the eye, which is an extension of the brain. You literally are projecting an image onto a screen, like what we're doing here. This is exactly what's happening. That projector onto this screen. Imagine that's the front of the eye, and this is the retina, which is actually a part of the brain. You literally put the image onto your brain. It's pretty wild. So a couple of pictures, different orientation. You can see, you kind of appreciate this cornea and the tenting that takes place. It kind of bulges out a little bit over even the white of the eye. You can see the iris. You can see this opening. The front part behind the cornea to the front part of the iris, this is known as the anterior chamber. Anterior chamber, and it's filled with what we refer to as aqueous humor. And then behind the lens is the posterior chamber that's filled with vitreous body. And when you did your sheep eyeball dissection and you punctured and it went, right? Most of that came out was vitreous body, right? Unless you stabbed it right in the front, but most of you kind of went through the main meaty part of the eyeball, which is the back of the eyeball, the posterior aspect. That would have been the vitreous body. Now, the lens is connected via these suspensory ligaments, and they're connected to the ciliary muscle, which actually controls the shape of the lens, allowing for refraction of light to be dialed in so that you can focus the image on this particular screen, which is your retina. You can see up here in the upper right, scanning electron micrograph. Here's the lens. Here's the suspensory ligaments. I just think that this picture is nice to see the number of suspensory ligaments that manage the lens, because this diagram makes it look like you have like 6 on one side and 7 on the other, right? But it's actually like the spokes of a wheel, right? It's all the way circumferentially around it, flattening the lens or allowing the lens to get thicker. So the neural apparatus. the neural apparatus is towards the back of the eye. That was the optical apparatus that we were talking about. The neural apparatus is this retina. This is the outgrowth of the telencephalon. I don't know if you remember that terminology from the central nervous system when we talked about the different embryonic regions of the brain. So the vitreous body, the back of the eye, that fluid, the front and the back, keep the eyeball inflated. But it's really important for the back of the eye to be inflated because it's pushing onto the retina, creating it to be a nice flat surface. So when the image is projected, that image is actually clean, right? You can imagine if the screen is like crumpled or folded, it doesn't have as clean of an image as if you actually have a nice, tight screen mounted on the wall for your, poolside movie or whatever it is that you're trying to broadcast. Now, on the back of the neural apparatus, we've got a couple of different structures. So we've got the fovea centralis. The fovea centralis literally means central focus point. That has the highest density of cones, which are for high visual acuity or color vision. Cones for color, CC. The fovea centralis is the highest density, which is about in the middle of the back of the eye, right here. Now, not far away from it is what we refer to as the macula lutea. And this macula lutea is a patch of sensory cells that kind of gives feedback back to the vision cells that we'll look at here in a second. And then the optical disc. The optical disc, which is located at some distance away from the fovea centralis. This is actually where the nerve leaves the eyeball. The optic disc is the point of entry for nerve fibers and blood vessels that leave the back of the eye. And so this picture that's shown here, it's not going to work for you to look at this screen. You have to look at your screen. But what you're going to do is you're going to cover your right eye and you're going to look with your left eye at the X. And then you're going to move closer to the screen and stare at the X, but out of your peripheral vision, that red dot will disappear. And right at that moment that it disappears, it'll reappear if you go forward or back. But right where it disappears, that's where that image is actually being projected onto your optic disc, which is known as your blind spot. Okay, so try it at home with your pad, okay? With your iPad or your tablet. It won't work here because you can't really move forward, right? You got to do it with a screen. But anything that actually focuses onto this point, it's devoid of sensory cells because that's actually the pathway where all the nerves and blood vessels are coming in and out of the eye. So dilation and constriction. We talked about this a little bit when we looked at some of the earlier units, but we've got pupillary constrictors and pupillary dilators. The pupillary constrictors are made up of circular smooth muscle, and the pupillary dilators are made up of smooth muscle that radiates like wheels of a spoke. And the purpose of these is to actually change the size of the pupil. And we did this exercise where we shut out the lights. Nobody was standing, so nobody was at risk of falling down, so I could still do that activity. But this happens, changes in size happen when you get changes in light intensity, right? Remember, we shut off the lights and the pupils got really big. You turn on the lights, the pupils get small. So you have constrictors that will constrict the size of the pupil. You have dilators that will allow more light in. So the other piece to talk about here is looking at the difference in the shape of the lens. So you can see a thin lens up top. You can see a thicker lens on the bottom. The picture on the top is where the lens will flatten so that you can see things further away. On the bottom is the lens will thicken or relax so that you can see things close up. Now, we have a number of different problems that we're going to get to with vision here in a second. But before we do that, we kind of want to talk about what the lens is doing, because the lens is actually bending light. Now, contrary to popular opinion, the lens actually doesn't do most of the work. What bends most of the light that comes into the eye? The cornea. Nicely done. The cornea bends most of the light as it comes into the eye, and then the lens does the fine tuning. So the cornea is kind of like the macro, and then the lens is the micro adjustment. Now, the cornea is really important, not just because of its ability to bend light, but it actually serves as a protective barrier. And the cornea is made up of a protein tissue, and that protein tissue of the cornea, that clear part, can become UV cross-linked as you get older, just like all proteins become. So as you're exposed to UV light, the cornea, the proteins in the cornea, as they cross-link, we gave this illustration in the very beginning of the semester with an egg, right? It's made up of protein, albumin, the white of the egg. And when it's non-cross-linked, what color is the white of the egg, right? When you crack a raw egg. Nice and clear. As you cross-link it, what color does the white of the egg become? White. And then can you see through it anymore? So that's what happens as you get older, and you'll actually have spots of cross-linked protein in the cornea that you actually have to get removed, right? This is the same phenomenon that happens with your headlights on your automobile. It's made up of a plastic. UV light will cross-link the plastic. If you drive a vehicle that's more than 10 years old, can you see parts of your headlights that aren't clear anymore? They're kind of cloudy, right? It's the same thing that happens. So the cornea and cornea health is actually really important, but it's actually difficult to kind of keep it, sort of clear, if you will, as you get older. Okay, so cornea does more bending, but the lens fine-tunes the image. So you can kind of appreciate these n values, n equal to 1, n equal to 1.4, n equal to 1.38, n equal to 1.33. These are refraction indices. So an example of what a refraction index is, how many of you have ever cleaned a pool with the pool sweep? And you put the handle, you put long handle in the pool, and it literally looks like the pool thing bends, right? It's a clear pool, there's no ripples, nobody's swimming, and you're brushing the side, and you put your pool broom in there, and it looks like it's taking this monster bend. It's because the refraction index is different between air and water. So the moment it enters the water, there's a different refraction index for light, and it literally looks like it bends. So in the body, if air is 1, the moment it comes into the cornea, right, the cornea is 1.38, you want to keep everything around the cornea all the way to the back of the retina, or you're going to get this weird bending, and things are going to look crooked. And so you don't want air in the back and you don't want air in the front, because it would come through the cornea, go from 1.3, it would go to air at 1.0, and you'd have this pool broom bend. Then it would go through the lens and go through air again. And do you see what I'm talking about? So that's why you have the fluid in there instead of air. We could have inflated the eyeballs with air, but you'd have this wicked bending of light, and we wouldn't be able to see accurately. So the whole idea is you actually want to fine-tune this image to be right here focused on the retina. Now, when that doesn't happen, we get these different clinical issues that many of you in this room wrestle with, as do I. So we've got presbyopia. Presbyopia, that is the lens losing flexibility. Just a generic term for the lens losing flexibility as we age. Presbyopia is what's responsible for, as we age, you get to about the age of 40 to 45 and you start having trouble seeing things close up. It loses its flexibility and you start needing reading glasses. Hyperopia, farsightedness. The eyeball is actually a little too short with hyperopia, And the focal plane is back behind the eye. It's as if that image, this is blurry because someone needs to scoot the screen back, and then it would be in focus. That's hyperopia, far-sightedness. So the image is beyond the retina. Far-sightedness means you can't see things close up. You're far-sighted. You can see things far away, but you can't see things close up. Myopia, nearsighted. You can see things close, but you can't see things far away. So many of you that have glasses on right now, because you need to see the screen that's far away, you have a myopic problem, right? You have myopia or myopic vision, where you have trouble seeing far away, you're nearsighted. Myopia is nearsighted. Myopia, nearsighted, the focal plane is in the front, the eyeball is a little too long, and so you can see the corrective lenses here. This is a concave lens that you'll use to focus the image in a myopic situation on the retina, and contrary to that, a convex lens in hyperopic individuals to correct them to have the focal plane being right on the back of the retina. Astigmatism is a term that's referred to as a misshapen cornea, astigmatism. So if you have a misshapen cornea, most of the refraction of the light that's happening isn't really a lens problem, it's the cornea. And so you could have like a abnormal cornea on one eye, and the other cornea on the other eye is just fine. So in that situation, your lenses are different based upon the right versus the left, the one that has the astigmatism. Does that make sense? Okay, glaucoma. Glaucoma. What is glaucoma? Well, this is a group of eye diseases that can lead to blindness, which is very serious. And if it damages the optic nerve, then it's non-reversible. And so the eye continuously makes this fluid, this aqueous humor that drains to maintain healthy eye pressure. And when the back pressure of the eye gets too large, it puts pressure on this optic nerve, and that causes trauma to the optic nerve, leading into blindness. So we'll measure intraocular pressure of the eyeball, and there are ways to manage decreasing fluid production. There are surgical interventions to implant shunts, similar to when we looked at hydrocephalus, where you actually have to drain. There are glaucoma shunts to drain that fluid. I talked about the lens issues. We talked about the astigmatism. I talked about the cross-linking of the cornea as we get older, especially if you live in, areas with lots of sunshine. What is that disease called of the cornea where you get cloudy corneal tissue? Any idea? Cataracts. So very common in our geriatric population, our elderly population, to have cataracts removed and allow for vision. So it literally, they'll tell you, it looks like there's like a cloudy area that's, it's like your windshield has like fog on it. And that's that cataract that's basically cross-linked protein of your cornea. Okay. Questions before we get into the last little section of how we see, and then I'll hand out this bonus opportunity. Okay, this is kind of a cool section. So we basically have two main types of cells, right? We've got rods and we've got cones. Rods are for black and white vision, and cones are for high visual acuity, also referred to as for color vision. And there's three different types of cones. Now, this diagram shows you the direction of light is here. The back of the eye, or the retina, is at the top of the screen. And the neurons that go to the optic nerve are in front, which is almost counterintuitive. So the light literally passes through all of this tissue and hits your photoreceptors. So these are not chemoreceptors, and they're not chemical receptors. They're not mechanoreceptors. They're photoreceptors. They are receptors that respond to light. And the rods look like rods, and the cones, they look like cones. The rods are for low light visibility. The cones are for high light visibility. 3 different types of cones, 1 single type of rod. You have far more rods than cones. 6.5 million cones, 130 million rods. Rhodopsin pigment. So we're going to photo bleach a pigment. That's how we're going to see this thing. That's how we're going to see an image. The rhodopsin is a pigment that can be photo bleached, and then it goes through a conformational change. When it goes through a conformational change, it triggers an action potential. And then the photo bleaching wears off, it resets, and it can be photo bleached again. Okay, so that's what this is going. Rhodopsin is the pigment that gets photo bleached. So these rods and cones converge, and they converge on a limited number of cells, and these cells are called bipolar cells. So the photoreceptor cells in the back, they get lit up by light. They converge on fewer bipolar cells in front. These bipolar cells then converge on these ganglion cells. The ganglion cells send the signal to the optic nerve. So it goes, light comes in, hits the back of the eye where the photoreceptors are, then the action potential starts moving forward until it reaches the ganglion cells that move to the optic nerve. And those axons that collect from the ganglion cells, they actually converge and form cranial nerve 2, also known as the optic nerve. So kind of a picture of the rods and the cones, schematically on the right, and then a scanning electron micrograph kind of in the middle top. You can see the cone is kind of short and stubby, but it looks like a cone. You can see the rods are these column-like structures. The rods have rhodopsin, and we'll show you how that mechanism works in the last slide where it photo bleaches. And the cones have photopsin, and it has 3 different types. It detects a green, a blue, and a red wavelength. And it's difficult nowadays to kind of use these examples like televisions, but long time ago with TVs, even with like projection TVs, and maybe like your grandparents had one, you could see in the back of the TV, or if you had like an old tube display TV, if you got really close up, probably not good for you, but you could look at the screen like this, put your face right up against the screen, and you would see red, a red dot, a blue dot, and a green dot. And they'd be red, blue, green, red, blue, green, red, blue, green. So with red, blue, and green, you can see the entire visible spectrum. When you combine those wavelengths of light, certain will cancel out, and you can see the entire visible spectrum. So our color vision is based off of being able to detect only 3 primary colors. But we see the whole rainbow of colors of visible light. So we're going to use the rhodopsin example to talk about how this works. So you can see there's a dark cycle in the upper left, and then there's a light cycle kind of in the rest of the slide. We'll start here. So this rhodopsin absorbs a photon of light. When it does that, it goes through this conformational change of cisretinol to cisretinol over to transretinol. And that conformational trigger is what stimulates an action potential that tells you that you've seen a photon of light. And then what happens is it goes into a dark cycle and it regenerates. It regenerates and replenishes. So it's photo-bleached at first, and then it actually regenerates and is replaced. So like a flash, like from a camera, like a big flash of light, all of a sudden you're blind for a period of time, right? That's because all of the rhodopsin, or photopsin if it's in color, all of the rhodopsin has been photo-bleached. Every single one of them, a really bright light will photo-bleach all of them, and you're in a cisretinal state for a couple of seconds. And then it takes a little time for the photobleaching to fade before you can start seeing again. Okay. So retinol. What are some foods that are high in retinoic acid? Also known as like vitamin A. Carrots. So you've heard this there's this tale that carrots are good for your vision. Your mom wanted you to eat your carrots, right? That's where this comes from, is this retinol is derived from vitamin A, which carrots are a high source of. Cool. That wraps it up, folks. It's been a great semester. Hang tight. If you're taking exam 5, I got one more piece for you. Any questions before we go? For some of you, it may be the last time I see you for this semester. So I'll be around next semester. Hope you have a wonderful holiday. And come say hi next spring, okay? The rest of you I'll see on Monday for our last exam.